Imagine breaking light apart like a rainbow shimmering after the rain. That spread of light from red to violet is what we call a spectrum. It's a fundamental way the universe communicates with us, and the interplay between light and matter reveals itself beautifully through two key types of these luminous messages: absorption and emission spectra. These spectra, though they might appear opposite at first glance, actually share a common, intricate origin in the quantum behavior of atoms and tell complementary, profound stories about the universe around us. An absorption spectrum forms when light with a continuous range of wavelengths passes through a cooler gas. The atoms or molecules in the gas act like selective filters, absorbing precisely those wavelengths that match the energy gaps between their electron orbitals. This process leaves dark lines superimposed on the otherwise smooth rainbow of light. Each gap corresponds to a specific atomic transition. The sun's spectrum provides the classic example with its distinctive Fraunhofer lines, dark absences at the wavelengths characteristic of hydrogen, sodium, calcium, and other elements in its outer atmosphere. Crucially, absorption requires two components: a hot source generating continuous light and a cooler gas positioned between the source and the observer. In contrast, an emission spectrum emerges when a hot, low-density gas becomes excited and emits light on its own. Here, energized electrons in atoms jump to a higher orbitals before falling back down, releasing their excess energy as photons of specific wavelengths. Instead of dark lines on a bright background, we see bright lines of color against the darkness. Fireworks demonstrate this beautifully, with strontium producing crimson red, copper shining blue, and barium glowing green. Unlike absorption, emission doesn't rely on an external light source. The excited gas itself serves as the light emitter. The relationship between these spectra reveals profound symmetry in nature. For any given element, the dark lines in its absorption spectrum align exactly with the bright lines in its emission spectrum. Sodium, for instance, shows a dark line at 589 nanometers in the sun's spectrum, but emits bright yellow light at the same wavelength in a lab flame. This perfect correspondence confirms that both phenomena stem from identical electron transitions merely occurring under different environmental conditions. Astronomers leverage this duality to decode the cosmos. Absorption spectra unveil the composition of stars and exoplanet atmospheres, while emission spectra illuminate the chemistry of nebulae and interstellar clouds. Together, they form a complete picture of how matter interacts with light across the universe, whether through selective absorption or energetic emission. The next time you see a fireworks colorful burst or a prism's rainbow, remember you are witnessing the same atomic processes that allow scientists to analyze stars billions of light years away. Light's interplay with matter, manifested through these spectra, remains one of our most powerful tools for understanding the universe's composition and behavior. From the quantum realm to cosmic scales, absorption and emission spectra provide the vocabulary for nature's luminous language. Thanks for watching. If you found this video helpful, give it a thumbs up and don't forget to subscribe to the channel.